So here we're going to talk about electric current. So let's imagine we've got an electrical circuit. So here we've got a battery connected to a motor, and when we connect this up, what we call electric current is going to flow through the motor and it's going to cause it to turn. So we're going to have electrons flowing from the negative terminal to the positive terminal. And this current is made up of electric charge. And we measure charge as coulombs. So it's given the symbol C. So 1 coulomb is equal to about 6.25 times 10 to the 18 electrons. So coulomb is an awful lot of electrons. And we define electric current in units of amps, or simply just A, and this is given as coulombs per second. So 1 amp is 1 coulomb flowing in the circuit every second. And there's a really nice analogy here with a water circuit. So if we imagine a circuit of pipes with a pump that's able to pump the water around, so in this case if we're pumping water around this way, then it can drive some sort of mechanism, and the rate at which it's driven will be in part determined by the flow rate of water. So if we want to build this analogy, then we're going to have a particular flow rate of water, which we would probably measure in litres per second. So in this case, in the electrical circuit, we've got current measured in coulombs per second, and then in the water circuit, we've got current measured in litres per second. So Kirchhoff's current law is a law that we deal with when we've got nodes in an electrical circuit. So it's sometimes abbreviated as KCL. Now, a node in an electrical circuit is simply where we have a branching. So if we have a wire and this splits into two, if we've got some current flowing down this wire and then it's got two options or more than one option of where to go, then we call this point a node. So it's not where current simply goes around a corner. So this is not a node, but this is, and it can be where the current's got two or more options of where to go from a particular point when it's flowing. So this is a node and this isn't. So if we imagine we've got a certain amount of current, say 15 amps, flowing this way, then if we have, for example, 10 amps flowing this way, then we must have 5 amps flowing this way. So hopefully this is self-evident. The current can't disappear anywhere. So if there are 15 amps flowing this way, we must have 15 amps flowing out of the circuit. So if we know what one of the branches is, we're going to know what the other branch is. So we can state this mathematically as sum of I in is equal to sum of I out. So we can have any number of currents flowing in and any number flowing out. So mathematically we can express this generally as the sum of currents flowing into a node is equal to the sum of them flowing out. And as a convention, we also always say that if the current is flowing into a node, then it is positive, and if it's flowing out, then it is negative. So that way, if we add up all of the currents, then we should get 0. So if we say sum of all currents should equal 0 when we adopt this sign convention. And we can make a nice analogy again to a water circuit. So if we imagine we've got water at some particular flow rate flowing into a point, a node, where it has an option of where to go. So if we had 15 litres per second flowing in this way, then we had 10 litres per second flowing out this way, then we know we must have 5 litres per second flowing out this way. So here we're assuming, again as in the electrical circuit, that this current isn't going anywhere. So if current is flowing down a wire, it can't leak out, and if it's going into a node, a point where it's got more than one option of where to go, then that total current must flow through all of these nodes coming out. Okay, so a slightly confusing concept in physics is the idea of conventional current. So conventional current is the direction that a positive particle would take around an electrical circuit. So in this case, this is the positive terminal, so positively charged particles or charge carriers are going to flow this way around the circuit. And this is what we call conventional current. But we know in electrical circuits that the charge carriers are electrons, the actual charge carriers. So in this case, these electrons are going to flow this way around the circuit. But for all purposes of analysis, positively charged particles flowing this way around the circuit are exactly equivalent to negatively charged particles, or electrons, flowing this way around the circuit. So these two cases are equivalent, and there isn't really any system that you're looking at where thinking about positively charged particles flowing in the opposite way to electrons makes any difference. But you just have to remember that when we're talking about conventional current, this comes from the idea of the direction that positively charged particles would take, where we actually have electrons flowing around an electrical circuit. So this simply stems from the idea of a test charge. So if we're thinking about what's going to happen in any sort of system, so say if we've got a large charge and we want to know what's going to happen, we typically have two opposite charges. So if this charge was a similar size to this one, then this positive charge would have an effect on the negative charge. Whereas if we just want to imagine what's happening with the electric field generated by this negative charge, we'll just imagine having a small positive charge, and then the effect of this positive charge on this large negative charge will be negligible, and then we can imagine what's going to happen. So there's just a convention So this could be a large positive charge, and this could be a small negative charge. But there's a convention on, we call this test charge, being positive. So that leads to the conventional current being the direction that a positively charged particle will take.